Just a small technical difficulty. We'll be with you in just a moment.
Hey, good afternoon, everybody, and welcome to the 66th episode of How Do You Know? And I got to say, Paul, our producer, I love our new theme song and intro. That's just awesome. Makes me feel like I should be wearing a helmet and telling some kid named Luke that I'm really his father. So
Do you
great
really
stuff.
want to have
Apologize
that?
for being a little late today, folks. Let's jump right in. Science news.
So don't
And
forget
this
your
fits
book,
in
Dr.
with
Bard.
today's topic, a new theory of gravity. Some of you may remember the great dimming of the star Betelgeuse back in 2019. The absolute brightness of Betelgeuse dropped by 60%. And all of us were going, supernova, supernova. Didn't happen. Didn't happen. But there's a group of astronomers now have submitted a paper to the Royal Society of Astronomy, and their new theory is that what caused the dimming of Betelgeuse was in fact a wandering black hole that passed near their system. And their idea is that if a wandering black hole passed through the Betelgeuse system, that it would have raised a huge tidal bulge on the surface of Betelgeuse. And as you may know, red giants are red and giant because they've stopped fusing hydrogen in their core and they've switched over to a helium burning, which is much hotter, causes the star to inflate. And these large stars are very bright because they have a huge surface area to emit light. So they're very, very bright. And the brightness of the surface depends very much on its temperature and its distance from the core. And of course, if you raise a huge tidal bulge, you can pull a great deal of the star out away from the center, and that would cause the surface to dim. And they claim that modeling shows their hypothesis would account for the full 60% dimming. So we may never know, but if a black hole did pass through their system at Betelgeuse, there may be other effects that we can see with other telescopes. Maybe the Webb telescope can investigate. So this is a story we'll definitely want to watch. Today's program centers on a new theory of gravity. I was just talking about this with my students in my astronomy class today.
Dr. Barth.
Yes, sir.
Don't forget your book.
I will not forget the book. I will not forget the book. And I do have a copy right here. I've always got a copy nearby. And I hope you guys have a copy nearby as well. Star Mentor. Basically, if you are out looking in these winter nights and you're active doing astronomy, I'll tell you folks, one of the things we need to do is we need to have a plan when we go observing, because on these nights when the temperatures drop, winter skies are great for observing, but it's not the kind of summer night when you're going to go out with a cold beverage and a lawn chair and a telescope. I'm just going to gaze around and see what takes my fancy. When the weather gets cold, we want to go out with a plan. We want to have every minute being useful. And that's where a book like Star Mentor can do you a great service, because this book can help you plan your observations, learn the sky, learn to guide your telescope, learn what you're looking at. Bringing knowledge to the eyepiece brings wonder home. So Star Mentor, Setting Hearts Afire for Astronomy. We'll hope you'll pick up a copy and drop us a review today. And the other book of the week, because we sometimes bring up a book. Yes, I have a new book, or rather an old book. This is a manual of the slide rule by J.E. Thomson. Some of you may be familiar with J.E. Thomson. He did a whole series of mathematics for the practical worker. Wonderful books for learning how to use math in a practical way. And if some of you are into the arcana of the slide rule, this was the computer of long ago. This was the computer we used.
They built the SR-71
physics classes and chemistry classes.
Thing.
And if you're interested in that sort of thing, I just picked this up and I'm thrilled with it.
Dr. Barth.
And J.E. Thomson is one of my favorite technical authors.
Dr. Barth.
So back we go to theories of gravity. Again, just talking to my class this morning. And I said, we were talking about the sun-centered versus the earth-centered theory of the solar system. Two theories that coexisted for about 2,000 years until there was technology. Galileo's telescope brought enough magnification and light gathering power to settle the debate once and for all and disprove this earth-centered theory. But I told my students that although there were people who advocated a sun-centered solar system, for the most part, they were disregarded. Nobody wanted to hear what they had to say. Why? They were disagreeing with Aristotle, who was the Einstein of the ancient world. And I told them, I said, if you come along today and you say, oh, you know, Einstein's idea of gravity, I've got a better idea than him. Well, that means one of two things are true. Either you're a knucklehead and a crackpot, or you are one of the smartest people alive today. And so this idea of a different theory of gravity, what's called modified Newtonian dynamics, or MOND. And this was developed by an Israeli scientist, and his name is Mordehai Milgrom. And to the Milgrom family, if I'm butchering this man's first name, I'm assuming this is a Yiddish variant of the more anglicized Mordecai. But Dr. Milgrom basically came along in 1982 and 3, and he said, I have an answer to Vera Rubin. Vera Rubin, of course, was this uh, brilliant American scientist who found that galaxies don't rotate the way solar systems do. And Dr. Milgrom came along and he said, basically, friends, I have two proposals for you. And he said, mathematically, they're basically equivalent. He says, first of all, you could have a situation where gravitational force that's experienced far out from the inner core of a galaxy could be proportional to the square of centripetal acceleration. Newton says gravity is always proportional to centripetal acceleration itself. In other words, Newton says the gravitational force is what you need to hold a planet in orbit. You take the moon around the Earth or the planet Mars around the sun, however fast it's going, it's centripetal acceleration pulling inward. Gravity is just strong enough at that point to hold that planet in orbit. In other words, Newton says that gravity holds a planet in orbit. It's proportional to centripetal acceleration. Milgrom says, no, proportional to the square of that centripetal acceleration. The alternate idea is that force varies inverse and linear with the radius from the galactic center. Newton says it's the very famous inverse square law. Many of you have heard of the inverse square law. Oh, well, inverse square because if you get twice as far away, you experience a quarter of the gravity. 10 times farther away, you experience 1/100th. And it's the inverse square of the radius. And
we use that all the time when setting up lights.
Sound, light, magnetism, electric fields, all, as far as we know, follow the inverse square law. And you're correct. Lighting for camera work, for studio work, always follows the inverse square law. If you're going to learn about studio lighting, that's one of the things fundamental skills you have to understand and master. Yep. And Milgrom said, maybe it's inverse linear with the distance from the galactic center. Well, it turns out that if you look at Milgrom's MOND, or modified Newtonian dynamics, it turns out that it's only different under special circumstances. Maybe this starts to sound familiar to you. Milgrom says that it only works, MOND's only effective under very, very low accelerations, much, much smaller than anything we would see in a solar system. And the accelerations in our own solar system or on the Earth are far too great to show any MOND effects. Well, does that sound familiar? Does that sound like our discussions of relativity? It rather should, because with relativity and Newtonian gravitation don't differ unless you're dealing with very large masses like big stars or galaxies, very great speeds up near the speed of light, or very great accelerations, high gravitational fields, which equates to large masses again. And so we get back to when Apollo 11 was flying to the moon, and Collins, Aldrin, and Armstrong were on their way out to the moon, and they were being interviewed by a news correspondent, and the engines were off, and they were coasting through space on their way to the moon. And one newsman said, "Hey, who's driving that thing anyway?" And I believe it was Collins who laughed, Michael Collins. He laughed and he said, "Isaac Newton's driving." In fact, when you want to send a spacecraft to Pluto or Mars or Jupiter or Mercury or to the moon, you don't really use relativity at all. The spacecraft don't go fast enough. And second, the gravitational field around the sun isn't big enough to make relativity, well, relevant. And we just don't use relativity for these relatively slow, relatively short travel distances, just, say, flying from here to Jupiter. And the same way with if we look at satellites orbiting the Earth, we don't use relativity. The only time relativity comes up in orbit is when we're dealing with GPS satellites. Because with GPS satellites, the satellites are moving fast enough, 17,000 miles an hour, orbiting the Earth. They're moving fast enough that, in fact, we have to take account of relativity. Otherwise, our GPS signals wouldn't be accurate to more than about 100 meters. Not good enough to get you from here to there on a road map. And if we take a look at relativity in space, and we don't use relativity when we fly, navigating. And what's interesting, if we take a look, and I have one illustration for us today, and I'm going to go ahead and show us screen 2 with our lovely little diagram from today's show notes here. And we see, here's a basic little map where we're looking at accelerations and gravitational fields. If we take a look where we are in the middle, and this is not to scale because the area for Einstein relativity is very small, the area for MOND is very small, but where we live is in here in the center. If you're talking about a star system orbiting a galaxy far, far away, out from the galactic center, say out where, probably well past where we orbit, but out towards where maybe the outer spiral arms of the Milky Way or where the Magellanic Clouds orbit, there MOND takes hold. And if you go ahead and you move in toward the galactic core, or you deal with nearby a very large star or a neutron star or a black hole, now the gravitational field gets very, very large, and now Einsteinian relativity takes hold. But you can see this is kind of like, depending on where our acceleration is, that's where we depend on which theory of gravity we work with. And I'm going to see if I can stop sharing here. And there I am. I'm back on. And the interesting thing about MOND, does it play nicely with other theories? Well, no, it does not. One of the interesting things is that MOND eliminates the need for dark energy. And if you take a look at these maps and you say, gee, how much of the universe is dark matter? How much is normal matter? How much is dark energy? And it turns out when you look at these maps, normal matter like me, you, the earth, the sun, the moon, 4% of the universe. And a huge part of the universe is dark matter, about 25%, the remainder being dark energy. Well, the interesting thing is the MOND theory says, dark matter doesn't need to exist. And we take a look, and why do we hypothesize dark matter? And we go back to the work of Vera Rubin, American astronomer and astrophysicist. And she went ahead and looked at galaxies, and she was studying the rotation. She was in an era in the 1980s, 90s, and 2000s when she had access to telescopes that were big enough. She could look at redshift and blue shift. If you've got a galaxy that's orbiting, part of it is orbiting towards you, and part of it is orbiting, moving away from you. And so we can look at the different sides of the galaxy. We can get redshift and blue shift, and we can find out how fast the various parts of the galaxy are spinning or orbiting as you move away from the center. The expected situation here is that galaxies would exhibit what we call Keplerian rotation. In other words, they would fall in and they would go ahead and see that galaxies exhibited Kepler's second law of motion. Going back a little bit, we're big on science history in this program. Johannes Kepler, German astronomer, and between 1609 and 1619, he spent more than a decade actually formulating, but he spent about a decade publishing his three laws of planetary motion. And the first law says all orbits are elliptical. The circle is a very rare and special case that really doesn't happen in nature because it's not stable. And he said, gee, planets move slower. And he basically said the cube of the period is proportional to the square of the distance. We're not going to get into the math on this, but basically Kepler said the farther away you go, the slower you move, and therefore the longer your orbital period. And the third law was that planets sweep out equal areas in equal time, basically meaning as a elliptical orbit brought them toward the sun, a planet would move faster, and as it moved away from the sun's gravity would slow it down, and it would move slower as it moved away. And the second law was really the one Vera Rubin was interested here, because we take a look at planets in our own solar system. And again, we pick our planet as the benchmark. And so we say, gee, we have an orbital radius of 1 AU, and our period is 1 terrestrial year. And we go back and we look at Venus, which is about 0.74 AU, and it orbits in about 240 days. And Mercury is about 0.4 AU, and it orbits in about 88 days. We go out to Mars, we're 1.5 AU. It takes 2 years. Jupiter at 5 AU takes 12 years. It's slowing down. You see the slowdown effect? And we go out to Saturn, now at 10 AU, takes 30 years to go around once. And so it goes until we get to Pluto, 40 AU, 248 years to go around once. So Kepler says the farther out you are from the center of gravity, the more slowly you move and the longer it takes for your orbit to go around. All well and good. How many solar systems have we tested this on? Well, pretty much one. We may have enough data on exoplanets now to look and see. We know some exoplanetary systems with more than one planet. And we are getting to the point where we can look at other solar systems and say, do they follow Kepler's second law? We fully expect that they will. But Vera Rubin found that galaxies don't. In fact, what Vera Rubin found was that the motion of stars in orbit around the galaxy don't slow down as you move away from the center, which is a real interesting thing. Well, if they don't slow down, why not? And Kepler, remember, didn't know about Newton's gravity. Newton's gravity comes fully, 45 years after Kepler publishes his laws, 40, 50 years. And so Kepler didn't know about this. He didn't have gravity as a reason. One of the interesting things is Newton went and used the inverse square law to prove with gravitational force that planets should act the way Kepler described. So Newton's gravitation confirmed Kepler's second law, and Newton saw this as a great victory for his theory because Kepler was a very revered man and very brilliant. So Newton comes along and says, yeah, my gravitational theory proves Kepler was right and gives it a fundamental underpinning where it doesn't. Kepler's laws were derived simply from observations. I observe things work this way, and they follow this mathematical pattern. Newton came along and said, oh, I have a cause. My theory explains how gravity works, and out of that theory, quite naturally falls Kepler's first, second, and third laws. And so Newton said, once you understand gravity, Kepler's laws become, of course, they have to be there because gravitational theory creates that motion and determines those motions. So, as somebody says here, Pekka, we are accelerating in science that fast now that we must see everything with new eyes. Not even physics is static anymore. I quite agree with you, my friend. One day we'll have to do a show on stuff that ain't so. So many things I was taught as a young man that are no longer so.
Isn't that a song?
Sorry?
Isn't that a
Is that a
song?
song? I don't know. If you can
Yeah,
find
it's
it, Paul,
Weezer. It's Weezer.
I am not a master of modern music.
Sorry.
I like Mozart. I like opera. I like Wagner. Modern pop music, not so much.
It's not
So,
really. I guess it's 10 years old. So
okay.
okay,
No, if you
fair
can
enough.
find it, we can't play it. I'm sure we
Nope,
don't
you
have a
can't play
license
it.
for it, but we could put it in chat and people could find it on YouTube for themselves.
I guess
And that would be fun.
Pekka was expecting to ask a few questions. So,
Okay.
but maybe we hold them till the end, Pekka.
Sure. Of course. Yeah, we'll take questions at the end. I'll make sure we finish up in time.
It's
Uh,
okay.
so basically, Newton explains why Kepler's law works. And then Vera Rubin comes along and says, "Welp, guess what? Things don't slow down as you get farther away from a galactic center the way planets do. So galaxies orbit differently than solar systems, which seemed nuts. Why should that happen? Because gravity controls all orbital motion. There's no other attractive force we know of that has any effect whatsoever. And so people said, well, we've got this effect. We have to keep Newton enshrined as the perfect law of gravity. And so we will enter this mysterious substance called dark matter. And the idea is if there's a shell or halo of dark material and it's farther out than all the luminous matter, the star systems, then we can see this dark matter orbiting in a spherical shell could, in fact, create enough gravitation pulling outward that it could speed things up and it could create this effect. Now, interestingly, if you're going to have this effect, you have to have just the right amount of dark matter at just the right distance. In other words, somehow galaxies and their dark matter shells have to be fine-tuned. We're having Goldilocks visit, just enough more dark matter, not too little, not too much, exactly the right place, orbiting around so it doesn't fall in. And by the way, you can't see it. It doesn't interact with matter except by gravity. It doesn't interact with light. The only thing it exerts is a gravitational force. That's the only way we know it exists. And we think back in the history of science and we say, so it's invisible, we can't see it, it doesn't interact with anything except one particular way. And this starts to sound familiar to those of us who are historians of science. Enter the ether. And that's a diphthong there. The ether was invented to explain how light travels in a vacuum. When Newton thought about light, he said light's a particle. That's how it gets from the sun to the earth. And as a particle of light, a photon particle, will bounce off a red flower and somehow it enters your eye and strikes your retina and you see red. And it can travel through the vacuum between the sun and the earth because it's a particle. Well, when we started to think of light as waves, how does it get here? If you have a wave in water, it waves through the ocean. If you have a seismic wave through the earth, it waves through sound, through stone. And so waves have to have a medium. And so, this medium, what's the medium of light? If light is a wave, it must be the ether. It's massless, it's invisible, it doesn't interact with matter, it only affects light. It doesn't affect gravity at all. All it is a medium through which light travels. It must be very thin and very rigid because rigid mediums, like a tense violin string, causes the vibration to go faster, a higher pitched note. You tighten up the string and blink, 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 blink. The note goes up the scale, and we know that more rigid the medium we have, the faster waves travel through it. So this speed of light is really, really fast compared to sound or any other wave we know. So it must be incredibly rigid, and yet the Earth moves right through it without slowing down. If the ether created friction, the moon would have slowed down and crashed into the Earth. The planets would slow down and crash into the sun a long time ago. And so somehow it's massless, it's invisible, it's very rigid, and it doesn't affect matter at all. Just light. Well, along came two rabble rousers, Michelson and Morley, and they said, we have this great idea. We're going to measure light in one direction parallel to the direction the Earth is traveling through space, and then we'll measure the speed of light perpendicular. If we measure it perpendicular to the way the Earth is traveling, then the Earth is traveling this way through the medium, and the speed of light shouldn't change going forward or back if we're perpendicular to that direction. On the other hand, if we're measuring the speed of light, if we're going forward into the ether, we should see it slow down. And if we're going backward, then we should see a difference in speed. And if you're on a open train car and you and a friend are riding on an open train car and you're playing a game of catch, throwing the ball back and forth, up and down the railroad car, someone on the side of the road measuring the speed of the baseball with a radar gun would find, in fact, that when you were throwing towards the front of the train, the ball didn't seem as fast. And when you're throwing back the other way, the ball seemed much faster. And so the velocity of the train adds or subtracts to the ball. And Michelson and Morley said, we measure no such change in speed at all. No matter how we orient our apparatus, the speed of light is unchanged. Forward and back, it's exactly the same in every direction. Well, it took a while, but it sunk in that if the Earth is moving through the ether and we're finding no effect, then in fact, either the ether doesn't exist or it's attached to the Earth specially amongst all the things in the universe, and the Earth drags it along, which sounds back like, oh, the Earth is the center of the universe and everything rotates around us. Aristotle problem again. And so people quickly said, well, we can't have Aristotle again. The Earth is not a unique place, and this ether cannot be attached to us specifically. And so the only other idea is, well, the ether doesn't exist. There are other examples. The planet Vulcan, and I've mentioned this book before, Thomas Levinson, The Hunt for Vulcan, lovely book, recommend it to you, very readable. Mercury's orbit was known to be messed up. The perihelion of Mercury was shifting a fraction of a degree per century. And Laplace knew about this. We knew about this in the 1750s, and we had measured this effect, and people said, well, it must be caused by something. There must be a small planet closer to the sun, which is dragging Mercury around and messing up its orbit. And people spent more than a century trying to look for the planet Vulcan. And their idea was quite reasonable. They said, we'll go out during a solar eclipse and we'll look for it with telescopes, or we'll later on with cameras. They took photographs, and this thing had to be inside the orbit of Mercury because Mercury was the only planet affected. It had to be really small because it wasn't obvious. It had to be very close to the sun because we didn't see it just before dawn or just after sunset the way we did Venus and Mercury. And so people said, a solar eclipse, we can look right around the sun, we'll find this thing. Lots of people claim to see it, but nobody could confirm any of the sightings. We think some of them may have been asteroids. We don't really know. Some of them may just have been flaws in film. But basically, what came along is, this time again, a new theory. Albert Einstein. And he said, you know what? With my new theory of gravity, relativity, it's going to make just the sun's gravitational field as it rotates is going to affect the orbit of Mercury, pushing the orbit ahead, precessing the perihelion by a fraction of a degree. And he, like Newton, calculated Kepler's second law from first principles. Einstein's theory of gravitation calculated from first principles using only his ideas of gravitation, that in fact the effect on Mercury should be exactly what we see. And later on, during the great eclipse of 1919, Arthur Eddington and Frank Dyson went out, one to the island of Principe off the coast of Western Africa, the other into the Amazon. Both of them looked at the solar eclipse. And in fact, not only did they find no planet Vulcan again, but they showed that rays of light from different distant stars were bent around the disk of the sun. The sun's gravitational field bent the light exactly the way Einstein said it should, based on his relativity theory. So once again, we had this mysterious substance that we had said must exist in order to explain the anomalies in our observations. The anomalies in our observations must be explained by something. The precession of Mercury must be explained by something. The ether as a medium of light, well, we must have something to make the light waves travel in. And oh gosh, we see this now interesting non-Keplerian rotation of galaxies. There must be something out there to explain this. And so we came up with dark matter. And if you were going to say the theory of gravitation that we have today is perfect and adequate, then in fact, in order to preserve it, we have to invent this new thing. Some of you may remember the idea of Aristotle's Earth-centered system. The thing he could not explain was the retrograde orbit of the planets. The planets would normally go eastward, but then once a year for a couple of weeks, they would go westward, and then they would switch direction and go back prograde again. And Aristotle couldn't explain it. And Ptolemy came along and said, well, if we're going to keep Aristotle because he's perfect and he's a genius, we have to invent this new thing to explain what Aristotle's ideas cannot. And so he came up with the epicycles, right? One circle rotates around the other. We have a How Do You Know program on this. You can look it up. And the epicycles, goodness, we're seeing is a discrepancy in our observation. Didn't indicate that there was an unseen thing out there we needed to discover, but in fact it indicated in our theory that our theory needed to be corrected and adjusted. This is how we went from Newtonian gravitation to Einsteinian relativity. This is how we went from Aristotelian Earth-centered universe to a Copernican sun-centered universe. This is how we went from, the planet Vulcan must exist. No relativity explains it. And, the ether, we explained we're going to keep this theory of waves through a medium. And so, huzzah, we invent this thing called the ether. In all of those cases, the new thing we invented to preserve our theory turned out not to exist. And so it's a very strange situation. And the hunt for dark matter is still on. We've got the compact muon solenoid experiment at CERN in Switzerland. We've got the light dark matter experiment at Fermilab. We have the large underground xenon or LUX experiment operated by the U.S. Department of Energy. That's at a lab down inside a mountain somewhere in North Dakota, Colorado. We've got the Axion dark matter experiment, the cryogenic dark matter search at Fermilab. We've got the ice cube neutrino experiment in Antarctica and the alpha magnetic spectrometer. And we have the cold dark matter camera. We talked about that just last week. We're using it to hunt for asteroids now. And all of these experiments assume, one, our ideas about gravitation are complete and sufficient. And two, we're hunting for this unseen thing that people said we have to save the old theory. Past performance is no indication of future results, as the brokerage firms say. But in fact, throughout history, when we have invented these things in order to preserve our theories as we understood them, virtually every single time, what we found out was that, well, the theory was broken, not our observations. We needed a new theory. When we see these anomalies, we might need to adjust our theory, but maybe, just maybe, and often it's true, this is a window through which we can now peer and discover new science, new theories. And it turns out that our wonderful Israeli friend, Dr. Milgrom, may have in fact solved this for us already with the modified Newtonian dynamics. And we've talked many times about Karl Popper and about different philosophers of science. And new scientific theories don't take hold immediately. Copernican theory was around, and Copernicus was 50 years dead before Copernicus got a real champion in Galileo. And it was some years of research with the newly invented astronomical telescope before Galileo found data showing could not be in the center. It was impossible. And still, it took years after that. And I'll remind you that Galileo was declared heretic. He was forced to recant. He was in prison for the rest of his life because of his Copernican heresy, teaching that the earth moved and orbited around the earth. Si muove. Yet it moves, he said, rising to his feet, but he still lived out the rest of his days in prison. And he was declared heretic in about 1632. But don't worry, he was forgiven by Pope John Paul the Great in 1992. So sometimes these new theories, that's not like, pow, oh, here's a new theory. We're all going to accept it now. No, there's thousands of scientists who base their careers for decades and decades upon saying Newton and Einstein are right and complete. They answer all the questions. We just have to look at the book more carefully. We have to do more experiments. Maybe there's this mysterious invisible thing out there that's explaining our problem away. So many times in the history of science, we've found that the mysterious thing we invent to keep our theory working and limping along, in fact, does not exist. And this may be the case today with MOND. And so students in another 20, 30, 40 years may be learning about Milgrom and Einstein and Newton as a continuum of theories that explains what happens in both very low and very high acceleration situations. So this is another one of those bleeding edge of science. No, I can't give you an exact answer today sort of problems. And it's the thing that either gives you the itch to learn more or just makes you frustrated. And I'm going to go watch The Simpsons now because science is aggravating. Pekala says, I just read an article of space-time and speed that can be just the same as we call gravity. Yes, Pekala, this is called the principle of equivalence. And Einstein said that acceleration was the same as gravity. And his famous thought experiments, Gedankenexperimenten, if I'm saying that properly in German, the idea of the man in the elevator and the elevator drops and the man inside experiences weightlessness. Or the idea that a man in an elevator who's accelerating upward at 2 gravities of acceleration, in fact, everything to that person in the elevator seems like they are on a planet with an acceleration of 2g. So, yes, your article was right on the point. And yes, that's true. Paul, do we have some other questions before we wrap up today?
Not that I can see.
Okay. Well, I will encourage our audience to go out and look up some stuff on MOND. And please, for these lovely, lovely winter nights for observing, pick yourself up a copy of Star Mentor. I would love to hear from you. You can write to me at astronomyforeducators@gmail.com. And I would love to hear how you're doing with the Star Mentor book and learning to use your telescope and binocular, learning the sky. I just gave a talk last week at the Sugar Creek Astronomical Society, talking to them about how we recruit new people into our hobby of astronomy and set their hearts alight for observing. And it's so easy to do. Your telescope, your binocular are a party in a box, and I encourage you to take it out and set it up where others can find you and find the wonders of the nighttime sky. That's where we'll wrap up this week. We're working on some more topics for the next couple of weeks. When we get into early, after the first week or so of December, we'll go on hiatus for a while because I have semester exams to give and to grade. And the end of the semester workload is quite substantial. So as we did last year, we'll take a hiatus from mid-December through to mid-January, and we'll get exact dates for you coming up next week. We do plan to be here for the Monday before the Thanksgiving holiday for our American viewers and friends. Not everyone celebrates the American Thanksgiving. I know our friends in Canada celebrate it differently, and so do our friends around the world.
What's Boxing Day? Boxing Day.
Boxing Day is the day after Christmas, and that's uniquely that's a holiday unique to the British, the countries of the former British Empire. So I believe they have Boxing Day in England, Scotland, Wales, Canada, and Australia.
You would think
I'm not sure about.
You would think Boxing Day would fall after the day after Black Friday. You have to box everything up.
That would be the American version. And Boxing Day was different. And I'm not going to shoot from the hip on this one.
I don't know
kind
what
of
it
rude
is.
to explain someone else's holiday.
There's this machine. It's the Google machine. If you want to know,
it's the Google machine. And maybe we'll talk about Boxing Day if it comes up next time. Yeah. If you have a topic you'd like to have us discuss on How Do You Know, drop me a line at astronomyforeducators@gmail.com. And likewise, if you have a comment about the book or a question, give me a line. And please, if you've picked up your copy of Star Mentor, please give us a review on Amazon. And this is your old friend, Dr. Daniel Barth, wishing you clear skies. And we'll see you again next Monday. Thank you, everybody.